Hello everyone who's watching on YouTube. Since no one has joined the session in person yet, I'll be waiting for like 5-10 minutes to check if someone joined the session in person. Otherwise, we'll just get started. So we'll get started in like 5-10 minutes. Till then, I'll just mute myself. Hi Akanksha. So we are starting in like 5 minutes to see if someone else also joins the session. Okay, so I guess since no one else has joined the session, we can get started. So once again, just to reintroduce myself to whoever was watching on YouTube. So hello everyone, I'm Lakshya Saggi, the Discrete Maths Problem Solving TA for the Monday 6 to 8 p.m. sessions. And this will be our 12th session and like 12th and the final session for at least this semester. And in this session, we'll be covering problems related to like groups and generating functions and counting using generating functions. So yeah, and note that even though this is the last session for like the discussing the problem statements, there will be another session held which will be the summary session. And like I'll let you guys know the timings. It will get posted on the uh, announcement channel of the NPTEL portal itself. The timing of the summary session. Most probably it will be like next week sometime, and it will be a 1 hour session. But you will get notified about it on the announcement channel. So till then, maybe we can start discussing today's problems. So let me just share my screen and I'll start discussing. One second, there is some issue going on. I'm not able to share my screen. Okay, now I think it's working. Okay, Akanksha, is my screen visible? Can you let me know in chat? Because I was not able to share it earlier. Now I'm able to share it. Okay, it's visible. Thanks. So I guess we can get started. So once again, like I'll be assuming that you have gone through the lecture videos for today's session, but nonetheless, I'll just be discussing some basic introductions or basic revision for what the main new things which were discussed in the lecture. So the idea of groups was something which you guys may have or may not have heard before. So what do we mean by groups? So groups are usually denoted by a set and an operation over the set. Maybe I should mention this here itself. Groups consist of a set and an operation defined over the elements of and yeah. And maybe it would be better to say a binary operation defined over the elements of that set. So what do we mean by a group? A group consists of a set and a binary operation defined over the elements of that set. So for example, here like I have defined q comma addition. So this might be a group. So other than this, like this is not the only qualification, just a set and a binary operation is not the only qualification for it to be called a group. It should satisfy some further properties, which are so it should satisfy further properties, which are like these four properties: associativity, closure, existence of identity, and existence of inverse. Maybe I should write that such that the following four properties are satisfied. And what are the four properties? The four properties are the following. So this is something like which you guys should remember. Like this is not like this is a definition and not something which you can obtain by yourself. That for something to be called a group, uh, it should satisfy these properties: associativity, closure, existence of identity, and existence of inverse. So I hope everyone knows what these properties are. So this has been discussed in the lectures also, but associativity just means that suppose you are like doing an operation over three elements, then the order in which you perform the operation does not matter. This is what associativity usually is. Similarly, closure is something uh, that like suppose A and B are two elements of the set, and like let's say addition is the operation defined over that set, then A plus B should also be present in the set itself. So closure should be there, existence of identity should be there. So identity is an element E such that like suppose addition is the operation, then A plus E should be equal to A itself. And similarly, existence of inverse means that for every element A, there should exist an element A inverse such that A plus A inverse gives us the identity element. So I'm just fast tracking through this because I'm assuming that everyone knows this and I'm just revising it for you guys. So yeah, so these are the four properties which should be satisfied. And yeah, and how do we define order of a finite group? So a finite group is a group where like the set of elements is finite. Like this set, so group consists of a set and a binary operation, right? So the A set associated with the group should have a bounded size, and that's when we call it a finite group. And the order of a finite group is nothing but the number of elements in the group. So I hope this much is clear. Then just to brush ourselves up using these definitions. So this is a simple question, but we'll do it nonetheless. So which of the following is are true? So we have multiple options and we have to identify which of the following is a group, which of the following is not a group. So maybe we can go option by option. So let's do option A. So Q denotes so I hope everyone knows what Q is. So Q denotes the set of rational numbers. Q denotes the set of. So it's a very standard notation that Q used to denote the set of rational numbers. So the set Q, the set of rational numbers over the operation addition. So if we assume the operation to be addition and the set of rational numbers to be the uh, set associated, then we have to verify whether it is a group or it is not a group. So maybe, and how do we check if it is a group or not a group? We have to check if these four properties are indeed satisfied. So we should check this. So checking the four properties. So let's check the four properties. So the first property is associativity. So we know that associativity is true, like over addition is associative always. So yeah, so it is associative. And why is this true? Because uh, since A plus B plus C is actually always equal to A plus B plus C. So we can say that associativity holds. And what about closure? So closure is also true, and this is because like addition of two rational numbers is always a rational number, right? If one number is P1 by Q1, second number is P2 by Q2, then their addition is just P1 Q2 plus P2 Q1 by Q1 Q2. So since uh, sum of two rational numbers is also rational. Now, what's the third? Existence of identity. So existence of identity is also true because like what will be the identity for this? Like, would you like to guess, Akansha? I think it's a straightforward question. Like for this group Q comma Q and the operation being sum, what will the identity? So yeah, zero. Good job, Akansha. So since zero is the identity, and I don't think we need to like explain why it's this. And similarly, what's existence of inverse? So existence of inverse is also true because And why is the existence of inverse true? This is because uh, for any element x, minus x is its inverse. Yes, since for any element x in Q, minus x is the inverse. So, and minus x, like if x is rational, then minus x is also rational. So this is also always present. So minus x is the inverse, and so existence of inverse is true. So option A is true. Okay, maybe I should swap the order of the options. Yeah, I would like to discuss this option B first. So Q comma multi. So this is the multiplication. So the set of rational numbers with the operation being defined as multiplication. So is this a group? Like, what do you think, Akansha? Will this be a group? Like, we have to check these four properties for it being a group, right? Do you think these properties are being satisfied here? Okay, so Akansha is saying no. So good job, Akansha. So yeah, actually it is not a group. And why is this the case? Not a group. So first of all, like it can be checked, like we have to check these four properties, right? Actually, it can be verified that these three properties will hold, that associativity, closure, and identity is true. Because multiplication is associative over rational numbers, closure is because product of two rational numbers is also rational, and identity for this would be one, because like anything multiplied by one gives the number itself. But this fourth thing, existence of inverse. So this is also true for most of the numbers, because for any rational number of the form P upon Q, Q upon P would be the inverse for that number. But this does not hold for the number zero. So in this whole set, there exists just one number, which is the number zero, which does not have a inverse, because zero multiplied by anything gives zero itself and not a one. So that's why there does not exist inverse for all elements. Like zero is the only element for which inverse does not exist, and that's why this fails to be a group. So note that all the properties were almost true. Like associated, it can be checked that it is associative. It also has closure. It has associativity, closure, and existence of identity. Also, all non-zero rational numbers have an inverse. So note that almost all the four properties were being satisfied just because of that extra number zero being in the set of rational numbers. And this fails. But zero does not have an inverse, and hence existence of inverse is not guaranteed. So that's why this is not a group. Just because of this number zero, this is not a group. So this is why I want to discuss this option, because this is a subtle difference. And yeah. Similarly, if we go to option C, so option C says like Q comma minus is not a group. So if the set of rational numbers is Q and the operation being defined is minus, then this is not a group. So what do you think, Akansha? Will this be a group or will this not be a group if the operation we defined is subtraction? Like let's just check just the first property itself. So associativity. So do you think associativity is satisfied for like subtraction operation? Like we can check other properties, but I think closure will be there because like difference of two rational numbers will be rational. There would be, I don't think there would be any identity because uh, so yeah, like I don't think there exists any identity for like subtraction. And similarly, since there does not exist an identity, there won't exist any inverse also. And also associativity also actually fails to hold true because not a group as it is not associative. And why is this the case? And this is because A minus B minus C is not equal to A minus B minus C. So I hope you see why this is the case that this would come out to be something like A minus B plus C when we open the parentheses. But this would come out to just be equal to A minus B minus C. And so these two things are not always equal. So that's why it fails to be associative. So we know directly that it is not a group. Closure will hold in subtraction also. There won't exist any identity and there won't exist any inverse either. So it is not associative. It does not have any identity. It does not have inverse. So because these three properties actually fail to hold for this sort of thing. And that's why it is not a group. Yeah, so good job, answer. It is not associative. And I hope you understand why is this the case. Because this and this are not equal. And this is what associativity says, right? For three numbers, like order of computation does not matter. Like you would have computed this first or this first, and it should have come out to be equal. But here it is not the case. Okay, then. So now let's come to option D. So option D, so you can see that option D and option B are very similar. Like in option B, we said Q comma multiplication is a group, which we checked that it was actually not. But now we have made a little bit of modifications. We have said, okay, almost all properties were true. Just this property that uh, the existence of identity was not being satisfied just because of this number zero. So maybe let's just remove this number zero and then answer whether this is a group or not. So now, actually, you can just go through the arguments again. It will be a group, like because multiplication is associative, it also has closure, and there is also identity, which is one. And for all non-zero numbers, and for all non-zero rational numbers, we already know that there exists an inverse. If a rational number is p by q, then q by p is its inverse. So that's why this will actually be a group. It is indeed a group. And why is it the case? Because all four properties are satisfied. So I just wanted to point out that even though this Q multiplication was not the group, but was not a group, but we actually, if we remove this number zero, then it becomes a group. So yeah. So option A says that like it is a group. So we verified that it is indeed a group. Option B is not a group, so it is false. And option C is not a group, so it is true. And statement D is also true. So options A, C, D are correct. Options A, C, D are correct. Okay. Now let us move on to the second question. So second question says that let T be a group of 100 elements. Then what is the largest possible subgroup of T other than T itself? So okay, maybe I should. What is the size of the largest possible subgroup of T other than T itself? So T is a group. Let's say we already know that T is a group which has 100 elements. Then what is the size of the largest possible subgroup of T other than T? So like we know that a group is already a subgroup of itself, right? If T is a group, then T is also a subgroup of that group. But we are not looking at that. We are looking at some proper subgroups, like which are not exactly equal to T itself. So note that I hope everyone knows what subgroup actually means. So subgroup is just like if we define a group by a set of elements and an operation over them, then subgroup is uh, a subset of elements taken from the original set, such that they still satisfy the properties of the original group. So something like that. So any guesses, Akansha? What should be the answer here? So hint would be like if you've gone through the lectures, then the Lagrange, you would need Lagrange theorem for this. Okay, maybe I should discuss this. So, so we know that since we are given a group of 100 elements, hence order of T. So order is just the number of elements. So order of T is given as 100. Now consider any subgroup. So consider any subgroup H of T. And I hope everyone knows what Lagrange theorem is, so it has been discussed in the lectures. So Lagrange theorem actually says that the size of any subgroup of T, so for any group, the size of subgroup should be a divisor of the original group size. So what Lagrange theorem says is that by Lagrange theorem, order of H, so the number of elements in H should divide order of T. So this just means that order of H should always be one of the divisors of T. So this is what Lagrange theorem says, that for any subgroup, the order of that subgroup should divide the order of the original group. And so this implies that order of H should be a divisor of order of T. And what is order of T given to us? It is given to us as 100. So order of H should be a divisor of 100. And what are the possible divisors of 100? Possible divisors of 100 is equals to, what are the divisors of 100? They are like 100 itself, then 50, then 25 would be a divisor. Then the next divisor would be something like a 20, then a 10, then a 5, then a 2, then a 1, and also a 4, I believe. So 100 would be like something like 2 times 5. So 2 times 5 would be 2 squared and 5 squared. It should have 9 divisors. And so these are 9 divisors, yes. So these are the 9 possible divisors of 100. And now we want to see and we want to find the size of the largest possible subgroup other than T. So if we choose the divisor 100 as a subgroup, then this already is equal to T. Like T had 100 elements. So this subgroup also has 100 elements. So it is the group T itself. So we don't want this 100. We want something smaller than this, but the largest possible. So that would be the next divisor, which is 50. So the maximum possible number of elements. So the largest possible subgroup size would be 50. Maybe I should just write it now, since the number of elements of H can't be 100. As H equals T, in that case, the maximum possible number of elements of H is 50. So 50 would be the answer in this case. Akansha has already written in the chat the answer 50. So good job, Akansha. So yeah, this is the point. So I hope it is clear that just like Grant's theorem says that we the order of any subgroup should be a divisor of the order of the original group size, order of the original group, and now you can just list out all the possible divisors of the original order and find out the largest possible between something like this. Okay, then maybe we can move on to the third question. So third question says that the generating function for distinct partitions of X is. So I hope everyone knows what generating functions are and what are distinct partitions. So just to revise orally, so distinct partitions. So the number. So if we want to find out the number of distinct partitions of a number n, so distinct partition just means that we need to write the number n as sum of distinct natural numbers. So no natural number should get repeated twice. So let's say consider number 3. Then 1 plus 1 plus 1 is not a distinct partition because 1 gets repeated 3 times. But let's say the partition 1 plus 2 is a distinct partition because 1 or 2 does not get repeated in that case. So this is what. So we already know what are partitions, and the distinct partitions are just the partitions where no element gets repeated twice. So, and what's the generating function for this? This has already been covered in the lectures. So maybe I should just write it down and also explain it again a bit, like why is this the generating function. So note that if you want to write some number n as a form of distinct partitions, then what are the possible cases? Either the partition contains the element 1 or it does not contain the element 1. Note that it cannot contain two ones because in distinct partitions you can only have an element at most once. So either uh, one is contained or one is not contained. So this x to the power 0 term denotes that one is not contained, and this x to the power 1 term denotes that one is contained. Now similarly, we can see the number 2 if 2 is contained in the partition sum or not. So if 2 is not contained, then we use x to the power 0 term to denote it. And if 2 is contained, then we use x squared to denote it. Because note that when we multiply, the powers will actually get added. So in this case, there will be a contribution of 2 in the powers, and in this case, there won't be any contribution of 2. Similarly, we check the contributions of 3. 1 plus x, 1 plus x squared, 1 plus x cubed. 1 similarly, contribution of 4, 1 plus x raised to the power 4, and so on. This is what we call a generating function for discrete partition. And note that so maybe I should write this in. And so the for any n, the number of distinct partitions would just be coefficient of n in the expansion of this polynomial. So this is an infinite polynomial, but if you just want to find it till n, you can just end it at something like 1 plus x to the power n, because the term n plus 1 or some higher term cannot occur in like a sum of, like, if a number n plus 1 appears, then we can't make the sum n using a number n plus 1. So that's why you can end it till here, but I'll just denote it by it going on till infinity, something like this. So this has already been covered in the lectures also, that this is the generating function for distinct partitions of n. And it was also covered that this actually can also be written in the following manner, that if you multiply both sides by 1 minus x, then you obtain something like if you multiply and divide this by 1 minus x, then what happens is you obtain 1 minus x squared divided by 1 minus x. So what I'm saying is you can write 1 plus x as 1 minus x squared divided by 1 minus x. And then you get something like 1 minus x squared times 1 plus x squared divided by 1 minus x. And then that becomes 1 minus x raised to the power 4. So what I'm saying is Maybe I should show it in form of an equation. So this has already been covered in the lectures, but I'll still like to cover this because I think it's a pretty neat thing. Yeah. So this can be written as 1 minus x times 1 plus x times 1 plus x squared one plus x cubed and something like this. So yeah, so 1 minus x. So the original term we divide and multiply by 1 minus x. So something like this. So I've just written fx as something like this. And now this becomes 1 minus x squared. So maybe I should just copy this thing. This is actually equal to 1 minus x squared. This 1 plus x, 1 minus x, and this. So wait. So this becomes 1 minus x squared, 1 plus x squared, 1 plus x cubed. And again, here we have 1 plus x raised to the power 4. And like so on. So the powers now keep increasing. Like x squared, x cubed, x to the power 4, x to the power 5, and so on. And now what do? We again check this product, like this 1 minus x squared times 1 plus x squared will become 1 minus x raised to the power 4. So this will become equal to 1 minus x raised to the power 4. Maybe I should just put it here. And yeah, remove this thing. And one plus x raised to the power 5 and 1 plus x raised to the power 6 and so on. So x cube, x4, x5, x6, and so on. And so we have something like 1 minus x raised to the power 4 times 1 plus x cube, 1 plus x raised to the power 4, 1 plus x raised to the power 5, and so on. So now this 1 plus x cube cannot be multiplied with 1 minus x raised to the power 4 directly. Note that these two terms can be multiplied, but this one, we want to remove this 1 plus x cube from the numerator also. So then we multiply and divide by 1 plus x cube now. And it becomes something like this. This becomes equal to. So let's say I multiply and divide it by 1 minus x cube. And now this 1 minus x cube and this 1 plus x cube will actually give me what I want. So maybe maybe I should move it to another line. So something like this, and this will give us 1 minus x cube, 1 plus x cube will give us something like 1 minus x raised to the power 6. So this will become something like 1 minus x raised to the power 4. This still remains. And this becomes something like 1 minus x raised to the power 6. And so these two terms come, and then 1 plus x to the power 4, 5, 6, and so on. And now what can we do? We can again use this 1 minus x raised to the power 4 and 1 plus x raised to the power 4 and make it 1 minus x raised to the power 8. So this will become something like 1 minus x raised to the power 8. Then we'll have a term of 6, 1 minus x raised to the power 6, 1 minus x raised to the power 8. But we'll need to multiply something with 1 plus x raised to the power 5. So we'll multiply 1 minus x raised to the power 5. And this will become something like this. Okay, we add in the denominator the term 1 minus x raised to the power 5. And in the numerator, we add the term 1 minus x raised to the, okay, maybe I should just write it down. this will become 1 minus x raised to the power 8. And here I multiply by 1 minus x raised to the power 5. So actually the pattern being observed here is these terms. So these terms, so now 1 minus x raised to the power 5 and 1 plus x raised to the power 5 will get multiplied. And this will give us 1 minus x raised to the power 10. And so these, the terms of the form 1 minus x raised to the power something will keep on increasing. And these terms will, like, as if x is very small, these terms will tend to 1. Right? So actually, and in the denominator you can see the pattern here is, so 1 minus x raised to the power 1, 1 minus x raised to the power 3, 1 minus x raised to the power 5. And when you continue this pattern, you will observe that all the odd numbers powers are coming in the denominator. So if you continue this procedure, maybe I should like this. Yeah. So dot 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 that you continue this procedure, you will obtain something like 1 in the numerator, because 1 minus x raised to the power infinity. So 1 minus x raised to the power something, and that something will be very large. And if x is like, let's say 0.5, then x 0.5 raised to the power infinity will give us 0. So we can just ignore this. And in the denominator, we'll obtain terms like 1 minus x cube, 1 minus x raised to the power 5, 1 minus x. So now this pattern of odd numbers will continue. That 1 minus x raised to the power 7, and so on. So this is also a possible generating function for distinct partitions of x. So you can write the generating function either in this form, which is like 1 plus x, 1 plus x square, 1 plus x cube, 1 plus x to the power 4, and so on. Or you can write it like this also. That multiply and divide by 1 minus x and something like this. And this gives us this form also. And note that this is also the generating function for like odd partitions also. What are odd partitions? The partitions where the numbers involved are only odd. So I hope everyone remembers. But that's like, this is the high level idea by which we obtain the result that distinct partitions of n is actually equal to odd partitions of n. So this has also been covered in the lectures, but this is the high level idea. And so this is also a generating function for distinct partitions of n. So this is also a possible answer, and this is also a possible answer for generating function of for distinct partitions of n. So yeah, I hope I made a bit of sense to everyone. If so, then maybe we can move on to the next question. This is a bit like not too involved because you have already seen it in lectures, but still this requires some thought, and I personally think it's very good. Yeah. Now let's move on to the fourth question. So fourth question says that for a path graph of P7, in how many ways can you color this graph with 4 colors so that no two adjacent nodes have the same color? So we are given a path graph. So path graph just consists of like 7 vertices in a line. And now in how many ways can we color this graph with 4 colors so that no two adjacent nodes have the same color? So maybe I should just first mention what a path graph is, although I assume that everyone knows this already. That's it. A line graph having 7 vertices. So let's say the vertices are V1, V2 till V7. Right? And now we want to see in how many ways can we color these vertices. So it's easy to check that initially if we are coloring V1, then the vertex V1 has 4 choices. Okay, V1 has four choices because there are four colors by which you can color. But then if you color V1 by let's say color 1, then the vertex V2 will have only three choices. And why is this the case? Because now V2 cannot have the same color as V1. And they share they share an edge, so like they must have different colors. Now similarly, if we come to V3, what happens to V3 is that V3 has an edge right now to only V2. So it cannot have the same color as V2. So that's why, like, if V2 has one color, then V3 cannot have that color, but other three colors are available. So again, V3 has seven choices, and like similarly, like you can obtain that V4, V5, V6, V7, all actually have three choices. So like first V1 only had four choices, and then all the remaining have only three choices. So yeah. And this has been covered in the lectures also, like in the name of chromatic polynomials, which says that a chromatic polynomial for a line graph is something like lambda times lambda minus 1 raised to the power n minus 1. But I usually like to not remember those polynomials, but rather explain it explicitly, like why is this the case. And now, so the total number of ways in which we can color is hence answer is just the product of these ways because these choices are independent. So it will be something like four times. So the V1 had four choices and the remaining six vertices have three choices each. So this will be something like four times 3 raised to the power 6. So this will be our final answer. So I hope this is clear. Like this is a very basic company calculation. But yeah, this is how we do it. And now we have fifth question. So fifth question is again like a simple question based on groups. So note that Z7 is a group and like this is a notation. If we are given a notation, let's say ZP, Z underscore P, then it denotes the set of integers as the integers from 0 to P minus 1. And the operation defined with respect to that group being the addition modulo P. So like Z7 means the set of integers modulo 7. And so addition would be modulo 7 also. So like what I'm trying to get here is like the number of the elements of this group will be just the elements like 0 to 6 because we are taking modulo 7. So the only possible remainders when dividing by 7 are 0 to 6, right? And addition will also be modulo 7. So let's say we have two numbers 6 and 6. Then their addition should actually give us 12. But 12 modulo 7 is just equal to 5. So for this group, 6 plus 6 will actually give us 5 if we are considering the group Z7. So this is the group which we are talking about. And now the question just simply asks us what are the elements of the group Z7. So as I already told, the elements of the group are nothing but like of a group ZP will be the elements from 0 to P minus 1. So here the elements will be like the elements from 0 to 7 minus 1, which will be just 0 to 6. 0, 1, 2, 3, 4, 5, 6. These will be the elements of Z7. A pretty straightforward question. Okay, now comes an interesting counting based question. So the question says that for word anaconda, how many unique words can be formed of length 5? So note that we are given this word anaconda and we want to find out the 5 length words which can be formed using the maybe I should. From the word Anna. Maybe I should write it from the word. So we have to pick like 5 letters from this anaconda word. So this contains only like 1, 2, 3, 4, 5, 6, 7, 8 alphabet. So it contains 8 characters. We need to pick 5 of them, and we need to see like how many unique words can be formed using those characters. So a naive way, what one can do maybe is like say that okay, we need to choose. So there are 8 characters. We need to choose 5 of them. So we can choose 5 of them in 8 choose 5 ways, and then we will have a word of length 5. And now we want to update all possible words, so we'll just permute it using like multiplying it by 5 factorial. So one might argue that the answer is 8 choose 5 times 5 factorial. But that will actually be incorrect because there are some repeated words here also, right? So this A occurs 3 times. So that's why what happens is if among the 5 letters you choose, the letter A occurs twice, then you will have to divide 5 factorial by 2 factorial also, right? So there will be multiple cases which you'll have to handle here. So there will be a lot of casework involved that while choosing these words of length 5. So one case would be with there are just 2 A's. Second case would be there are 3 A's. Third case would be there are like no A's and so on. So some casework would be required if you do counting directly. And when you are like writing down a lot of cases, it might happen that you might miss some case and because of which a mistake may occur. So usually for these kinds of questions, we prefer generating functions because like generating functions also capture the same thing, but they are just basic mathematical multiplication. So it's less likely for us to do a mistake. So what I'm getting at here is like this has been discussed in the lectures also, but I'll still like try to make everyone understand what I'm trying to say. So let's just see how many times does the word A occur. Uh, let's write down the frequencies of different alphabets in the word anaconda. So A occurs, how many times A occurs? 3 times. The alphabet N occurs 2 times. This contains 1, 2, 3, 4, 5, 6, 8 characters. So N occurs 2 times. Then C occurs once. Then O occurs once. And N occurs once. So this will give us 3, 5, and 8. So yeah. So these are the frequencies of different alphabets. And now what we want to find is, so one might originally say that, okay, let's pick, like if we have to pick 5 words out of these. So case one would be, let's just pick 3 A's and 2 N's. And in that case, the number of words which we can make would be just 5 factorial divided by 3 factorial, 2 factorial. Another case would be pick 3 A's once and like 3 A's and no N's, in which case like you can pick C and O, and then the answer would be 5 factorial by 3 factorial. And so like you take these different cases and add them up. But this might be a like bit tricky because you might miss some cases. That's what I was getting at. So what we instead do here is consider the generating function. And what do we have as a generating function? Following generating function. So f of x is nothing but 5 factorial times. So if we have been given this a, then we write down. So what do we do here is we have to make the length 5, right? So for a length n, we can see that if there occurs 1a, if there occurs 2a's, if there occurs 3a's, if there occurs no a's, and so on. So this one corresponds to like x raised to the power 0, which says that there occurs no a's in these 5 letters which we pick. Similarly, x raised to the power 1 denotes that exactly 1a occurs in the 5 letters. Similarly, x square will denote 2a's occur. But as soon as exactly two A's occur, we'll need to divide the number of permutations by 2 factorial. Because like we need to avoid repetitions because we just want to find unique one. And similarly, if three A's occur, then we'll need to divide it by 3 factorial. So this part was coming from all the A's. Similarly, from all the N's. So there are two N's. So again, we take this expression. And it can be seen that if no n occurs, then we have x raised to the power 0. If one n occurs, then it's fine. If two n occur, then if two n's occur, then we need to divide by 5 factorial. And nothing else is needed because there are just two n's. And now for these three numbers, they just occur once. So we just need to write it 1 plus x. Because either they occur or they don't occur. And they occur like these are three numbers, so this will be something like 1 plus x raised to the power 3. So what I'm claiming is this generating function, this 5 factorial times this, in this, the coefficient of like x raised to the power 5 will be the answer which I'm looking for. Then our answer is equal to the coefficient of x raised to the power 5 in f of x. And I hope this is clear, like why is this the case? Because like I think this kind of question we already had discussed last time also, and this has been discussed in the lectures also. 1 second, guys. I'll have to mute myself. Sorry for that. So you can just see that suppose we pick like two A's and three A's and two N's, then this term x squared times 2 factorial and okay, 3 A's and 2 N's, then this x cubed by 3 factorial times x squared by 2 factorial will give us that term x raised to the power 5 divided by 3 factorial 2 factorial. And we'll multiply it by 5 factorial. So that will give us the number of A's when we have 3 A's and 2 N's. Similarly, all the possible cases will be handled using this generating function. And now we just need to find the coefficient of x raised to the power 5 in this generating function. And note that now we don't need to like write all the cases by ourselves that, oh, 3 A's occur, 2 A's occur, 1 A occurs. Everything is just being handled by this generating function. And that's why it sometimes becomes a much neater way, because it is not up to us now to write down all the cases. It is just up to us to perform all the calculations. And usually we make lesser calculation mistakes than the mistakes we make while making cases. Okay, so maybe we can just, should I try out finding out the coefficient of x raised to the power 5 here? Okay, this will be a bit involved. 1 plus x cubed. Okay, yeah, maybe you can try it yourself. I don't want to get into calculating all of this. So you just need to expand this polynomial to find out the coefficient of x raised to the power 5. And as soon as you obtain the coefficient of x raised to the power 5, that will be your answer. So try it yourself. So I hope this is at least this process is clear. Like how did I write down the generating function and so on. So is it clear, Akansha? Like if there's at any point of time, if there's any doubt, then feel free to ask me in chat. Like, okay, it's clear. Nice. So like if you don't ask me, then I'll have to assume that it is clear. And this might not necessarily be the case. So yeah. Then maybe we can move on to the seventh question. So seventh question says that we just have to state whether this statement is true or false. So the statement claims that PO of n is the coefficient of x raised to the power n in the function 1 plus x squared till 1 plus x raised to the power n. So what do you think, Akansha? Is this so PO of n? I hope you know from lectures that this is like the number of odd partitions of n. Like if you write n as sum of like n, if you write n as sum of like natural numbers, then all the natural numbers should be like odd, and we have to find the number of ways in which this sum can be written. And then we are saying that PO of n is actually the coefficient of x raised to the power n in this. Okay. So Akansha is saying that this is true because PO of n is equal to PD of n. So good job, Akansha. So you're actually correct. So as I discussed already, guys, that this function 1 plus, so there are two ways to look at it. So this function 1 plus x square, 1 plus x cubed till 1 plus x raised to the power n. So this function is nothing but somewhat of this function, right? Like as we already said that 1 plus x square till like you can end it at 1 plus x raised to the power n, or you can continue it till infinity. It does not matter for the number n. So if we continue it till infinity, then this is actually equal to this number 1 upon 1 minus x, 1 minus x cube, 1 minus x raised to the power 5, 1 minus x raised to the power 7, and so on. And this is actually the, from the lectures, you may remember that this is actually the odd partition generating function. Why is this? Because 1 minus x is just written, can be written as 1 plus x squared, and so on. And 1 upon 1 minus x cube can be written as 1 plus x cube plus x raised to the power 6 plus x raised to the power 9, and so on. Like this part denotes like finding out like using the ones. This part denotes using the threes. This part denotes using the fives. This part denotes using the sevens, and so on. So this is nothing but equal to this, and this is the odd partition generating function. So that's why this gives us the odd partition generating function. Also, another way to look at this is like this actually is equal to like the distinct partition function, like PD of n, which I gave here 1 plus x, 1 plus x squared, 1 plus x cubed, 1 plus x to the power 4, and so on. And it has already been discussed in the lectures that PD of n is actually equal to PO of n. So that's why this is true. So like maybe that's a simpler explanation. This is what Akansha has also written. True as PD of n is equals to this thing, and we know that discussed in the lectures that PD of n is equals to P n. So yeah, that's why this is true. So PD of n is P of n, and like this is, and this is what we want. So yeah, that's how we obtain this. Now moving on to the eighth question. The eighth question is, let A be a group with 70 elements. Then A cannot have a subgroup of cardinality. So we are given like multiple options, and we want to find out like which of the following options can never be a subgroup of the original group A. So again, in this question, like I guess you can already see that whenever we have this group and subgroup, like whenever we have to find out cardinality of subgroups, when we are given the cardinality of groups, like it's usually related to the Lagrange theorem. And here also, like it's related to Lagrange theorem that uh, all subgroups should the cardinality of subgroup should be a divisor of the cardinality of the original group. So here, like whatever be the cardinality, it should divide 70. And like 5 is a divisor of 70. So it may be a possible. We need not always have a subgroup of cardinality 5, but there can exist cases where there will be subgroup of cardinality 5. Similarly, 10 also divides 70. So that's why this is also okay. But 20 does not divide 70. So there can never exist a subgroup of 20 elements. Like it might be the case that for some groups, even a subgroup of 10 elements may not exist. But there will be some where there will exist 10 elements subgroup. But for 20, we are always sure that there will never exist a subgroup of 20 elements. I hope you get the difference that for this, we are always sure. And in this, in some cases, there may be a subgroup, there may be not be a subgroup. Like for all other cases, there may be a subgroup, there may not be a subgroup. But this question asks that which can never have a subgroup, like which of the following is never a possible subgroup. And that is only the case with 20. Like 20 is never a possible subgroup size for a group of 70 elements. So yeah, so option C is the correct answer, and Akansha has also written it. So good job, Akansha. I'll just write it down as by Lagrange's theorem. The order of subgroup should divide the order of the group, but 20 does not divide 70. So yeah. So I hope it's clear now. Then maybe we can move on to the ninth question. So ninth question says that Z6 comma addition, let's say Z6 divided over addition is a group. And by Z6, we just mean the like the group modulo 6, like the set of integers modulo 6. So what this means is like the elements will all be like 0 to 5, and this addition is also modulo 6. So like 5 plus 5 will be something like 5 plus 5 is 10, but 10 modulo 6 is 4. So in this group, 5 plus 5 will actually give us 4 and something like that. And now what we want is find out the inverse of 4 in this group. What is the inverse of 4? So whenever we need to find the inverse, we first need to find out the identity of the group. So in this, it is clear that identity of the group is 0, because any element added to 0 gives the element itself. And this is true modulo 6 also. Identity of the. So it can be seen that the identity of the given group is 0. And now, so what do we mean by inverse? By inverse, we mean a number which, when added to 4 modulo 6, gives us 0. So this is what we want. Like inverse is a number which, like for a number x, like x inverse is a number such that x plus x inverse gives us the identity element. And here the identity element is 0. So what we want is, so we want a number x such that x plus 4 modulo 6 gives us 0, which is the identity. So we want a number x such that x plus 4 modulo 6 gives us 0. And from this, and also what we want is this x should lie in 0 to 5. Yeah. One thing, like maybe I should not write down, but just that x will lie between 0 and 5. Like it would be one of 0, 1, 2, 3, 4, 5, because there are just 5 elements. So yeah. So from this we get like one might say that, oh, x is equal to -4 gives me the solution. But note that -4 is not a member of this group, because the members of this group are only the numbers from 0 to 5. So we have to find out the solution from 0 to 5 itself. And here, like you can actually see that setting x equals to 2 gives us the correct answer, because 2 plus 4 gives 6 and 6 mod 6 is 0. This implies x is actually equal to 2. Okay, so Akansha has also already written the answer as 2. So good job, Akansha. So, so the x is equal to 2 is the answer. And now let's come to the 10th question, the penultimate question for the day. So suppose we are given a complete graph with 11 vertices. Then in how many ways can we color this graph such that no two adjacent vertices have the same color? And we are given 26 colors. So a complete graph is a graph which has edges between all pairs of vertices. So maybe let's just write down this since the graph is complete. Uh, every pair of vertices has an edge between them. And what we want is no adjacent vertices should have the same color. And since every pair of vertices have an edge, so all pairs of vertices are adjacent to each other, which means that every vertex should have a different color. Like anytime two vertices have the same color, then there will be an edge between them, and so like it will not be a valid coloring. So this essentially implies that every vertex should have a different color. Every vertex should have a different color. Something like this is what we want. And now the problem just reduces. So we have 11 vertices. So actually we want to assign 11 different colors to these 11 vertices out of the given 26 colors. So the problem just reduces to assigning 11 different colors to the 11 vertices out of 26 colors. So what we have is like we can just select like out of these 26 colors, we just select 11 of those colors in 26 choose 11 ways. And then like since we can commute these colors among vertices, we multiply it by 11 factorial. So one way to count this would be 26 choose 11 times 11 factorial. So that is what I'm writing orally, but another way in which we can write it is that so first vertex, let's say we are coloring first vertex, it has 26 choices for colors. First vertex has 26 choices. But as soon as one of first vertex picks one of the colors, then the second vertex only has 25 choices because now one of the colors is taken. And now two of the colors have been taken. So third vertex only has 24 choices. And if this goes on and on, then the 11th vertex, the last vertex is the 11th vertex, it will be only left with how many choices? So so it will be left with 16 choices. So something like this. So first vertex has 26 choices, and this goes on to 11th vertex having 16 choices. And since all of these are like independent cases, so we'll have to multiply this to find out the total number of ways. Hence, the total number of possible ways is 26 times 25 times 24 times 23 and like which goes on to like 16. And note that this is like nothing but what I already told you also, like we choose 11 colors out of the 26 colors, which we do in 26 choose 11 ways, and then multiply this by 11 factorial because these colors can be permuted among vertices also, which is nothing but like 26 choose 11 times 11 factorial. Like something like this. And this can also be written as like what people like to call it the permutation, like 26 B11. So all of these are same things. So yeah, this is our final answer. So I hope this is clear. If so, then we can move on to the last question for the day. This is a bit of an interesting question. At least I like this. So, what this question says is that suppose we have an MMA event. So, let's say MMA is just mixed martial arts, like fighting tournament, in which N fighters are participating. And each game consists of a match between two fighters. So, in any one game of the event, like two fighters will be fighting between them. And no two, okay, maybe I should write it earlier. No two fighters fight each other more than once. So what might happen is, so each game consists, so we do not know the tournament structure. We just know the rules that someone is organizing a tournament where we do not know the actual tournament structure. What we know is that each game will consist of a match between two fighters, and no two fighters will fight more than once. So it may be possible that some fighters will never get to fight with each other, and some get to fight with each other. But it will never happen that two fighters fight each other more than once. And now for any tournament structure, which means that for any sequence of games, like okay, or okay, now maybe I should rewrite the question. Based on this, answer whether the following statement is true or false. And for the statement, this is the statement that okay, we are just given that each game will consist of a match between two fighters, and no two fighters fight each other more than once. We do not know the tournament structure, like if whether one fighter will be fighting, how many fighters the other fighter will be fighting, which fighters. We do not know anything about it. We just know these two things. That one game, like each game will have just two fighters, and like no two fighters fight each other more than once. They might fight each other zero times or one time. And now we have to answer this problem, that for any tournament structure, so any tournament structure basically means for any arbitrary sequence of games. So any valid tournament structure will be just a sequence of games defined by a referee or something like that. Suppose there are 10 fighters and just the tournament structure is only one and two fighters will fight each other once. Or let's say like all fighters fight each other exactly once, or anything like round robin elimination, anything can be there in the tournament structure. There will always exist two fighters who have played an equal number of games by the end of the tournament. So for any arbitrary tournament structure, the statement claims that there will always exist two fighters who have played equal number of games by the time the tournament ends. So this statement true or false? This is what the question asks. It is given to us that each game, like these are the only thing known to us. We do not know the tournament structure, but we want to say for any possible tournament structure, will this statement be true or false? That there will always exist two fighters who have played an equal number of games by the end of the tournament. So this is a fun question which I really like, and I would like you to think about it, Akansha, for a while. Okay, Akansha is already typing in the chat. Okay, so Akansha is saying that the statement is true because fights are from 1 to n minus 1 and fighters are n by pigeonhole principle. Okay, Akansha, you're on the right track, but note that it may be possible that a fighter fights zero fight also. Like, I have not said that every fighter needs to fight at least once. This is not true. A fighter, like, it may be possible that a fighter, like, the sequence of games can be possible that a fighter times fight zero times also. We are allowing that also. Arbitrary tournament structure means that a fight. It may be possible that a fighter even does not get to play. So I hope the question is clear. So suppose like, okay, if every fighter was playing at least once, then a Akansha says that the number of possible fights for a fighter are from 1 to n minus 1, because maximum a fighter can fight n minus 1 other people and minimum it fights 1. So there are n minus 1 possible numbers for each fighter, and there are n fighters. So there will exist at least one number which has two fighters. So that's why like at least two fighters will be uh, having equal number of games played if every fighter fights at least once. But what we are saying is this statement true even in the case if we allow that a fighter is allowed to be fighting 0 times? So Akansha, I hope the question is clear. So like I'll be muting myself. Like I want you to think about it for 4 or 5 minutes first. And yeah, so question is clear. So think about it for 4 or 5 minutes, and like when if you come up with the answer or any ideas like on how to solve it, then do type it in chat. Till then, I'll be muting myself. Just try to think about it yourself. Like if we are allowing like 0 fights also for one fighter, then what happens? And whatever arguments come to your mind. So you are on the right track. I'm giving a hint that you're on the right track, but you need to think a bit. And whatever arguments come to your mind, like you can just type it out and we'll see. So I'll be muting myself till you think about it. So any ideas, Akansha? Like, just mention anything which, if anything came to your mind, like any approach to see if it is true or false. Like, it is true, like you have already solved the case, like it is true if every fighter fights at least once. You just need to look at the case if a fighter is also fighting 0 times. So just think out in that direction, like what happens if a fighter is fighting 0 times? And still we have like all fighters have distinct number of games. Then what would be happening in that case? Try to think it for like a few minutes more because I think, yeah, you are already very close to the correct case. Okay, Ansha is typing something in the chat. Okay, so Akansha is saying like, okay, you think it's true because if one fighter fights 0 fights, then we have n-1 fighters and n-2 possible. Or all have 0 fights, then also 2 fights equal number of time. Okay, so I think you're on the right track, Akansha, but a, s- a slightly, I think there's a slight mistake here. So it's correct that again, if you have 2 fighters fighting 0 fights, then also the claim will be true that there will exist 2 fighters having equal number of games. So let's say one fighter fights 0 times. Then there are n-1 fighters left, but there are also n-1 possible numbers left, right? 1, 2, 3 till n-1. These are the number of possible fights which are left. 1 to n-1. And there are n-1 people left. So there are not n minus 2 possible people left, but n minus 1 itself. So what actually will happen is if you want that, every fighter should have different number of games, then this is only possible if one fighter plays zero number of times, another plays one number of times, another plays two number of times, and the nth fighter plays n minus one number of times. So this is the only way which I'm claiming, in which you can have that no two fighters fight the same number of fights. But now what I claim is this can never happen. Like maybe I should write it down. Uh, in the meanwhile, you should also think, like while I'm typing the argument down, you should also think like, why can this never happen? That one fighter plays zero fights, second fighter plays one fight, third fighter plays two fights, till nth fighter plays n minus one fights. Why is this case also not possible? I'm claiming that this is also not possible. So, and like that is why like this statement will hold true actually. Like this would be true. So answer is true, and like so first of all, like I'll be invoking your argument only, Akansha, and then like there will be a more involved. So now what we say is like suppose we do it by contradiction. So suppose we prove by contradiction. Like suppose the statement was false. What this means is that this implies that every fighter fought a different number of games, right? And but what we know is from Akansha's argument also, as there are n fighters, so we know there are n fighters, and each fighter can fight 0, 1, 2 till n minus 1 games. So one of these numbers for each fighter, and there are n fighters. And we want that every fighter should have a different number of games. So like this will only happen when one fighter will fight 0 games, one will fight 1 game, and this will go until one will fight n minus 1. Like one fighter will have to fight n minus 1 games, one have to fight n minus 2, till one having fighting n 0 games. And this is because these are only n possible numbers, like the number of games which can be fought are n possible, and there are n fighters. So each fighter will occupy one of these. But now I'm claiming that this claim is cannot be true. That like one fighter fights 0 games, one fights 1 game, one fights n minus 1 game. And why is this claim? Okay, so Akansha is saying that okay, Akansha is already written the argument, since that would mean all other fighters played at least one match with the person played n minus 1 matches. So none played 0 matches. Exactly, Akansha. So you are at the correct. Akansha, you have arrived at the correct answer, like the correct reasoning. So just writing down here again. So what Akansha is saying, I'll just paraphrase it. So this is what we know, that one fighter will fight 0 games, one will fight 1 game, till one will fight n minus 1 games. Now, but what we claim is this can't be true. But this can't be true as the nth fighter. The nth fighter is the fighter which fights n minus 1 games. Nth fighter fights n minus 1 games. And hence has to fight everyone else. Because one fighter cannot fight another more than once. So what this means is that if one has to fight n minus 1 games, then it will have to fight all the remaining players. But note that this is not possible, but there exists a fighter who does not fight anyone, or which is not possible, as there exists a fighter which does not fight anyone. And so we arrive at a contradiction. Hence, a contradiction. So the statement is right. Okay, so this was a cute like I like this reasoning also a lot. Like this is a one-line reasoning, but this is quite cute that if everyone fights different number of games, then nth fighter will have to fight everyone, but there exists a fighter who does not fight anyone. So that's why we arrive at a contradiction. So good job, Akansha. Like you arrived at the correct reasoning. This was quite nice. Okay, then. So I guess this was the last question for the day, and so like also the last question for these sessions, like at least for this semester. I'll also be taking a summary session of 1 hour sometime next week. I don't exactly remember the time. The timing will be posted on NPTEL itself, and I'll let you guys know in chat also when the session will be held. So yeah, but other than that, these so that will be a summary session in which I'll be like just going through the concepts which we covered over the course of 12 weeks. It will just be a 1 hour revision session, you can just say, before your final exams for the NPTEL. But these problem solving sessions, at least for this semester, have come for an end. Like this was the last problem which we discussed for this semester. Okay, so I guess so it was, I guess, very nice interacting with you guys, and like I hope to see you in like the summary session also, or the revision also. So once again, like thanks for joining, Gansha. Hopefully we'll see you in the next session also. Till then, goodbye. I'll be like stopping the screen and you can leave the session. Bye bye.